Yes, sir.
Okay. And is my screen visible? The full screen mode?
Sir.
Yes, sir.
Thank you. So in this session, we're going to discuss convolutional neural network, okay, which is another framework, the artificial neural network, like it's one of the deep learning framework, convolutional neural network. Okay, so actually thought of not covering this, but later I felt that this is one of the thing that if we miss this, it's not good. So let us cover this as well, convolutional neural network. Okay, so in this session, we're going to deal with machine learning models versus the convolutional neural network. Okay, and then drawbacks of the fully connected neural network that we had discussed in the previous session, yesterday's session. So what is the drawback of the fully connected neural network? Then we'll discuss the foundational concepts of the convolutional neural network. Okay, so convolutional, padding, stride, pooling, etc. We'll just go through some of the classic nets also, applications of CNN as well. Okay, so this is the agenda for this session. All right. So let us start the session. What is the difference between the traditional machine learning models or the pattern recognition models versus the convolutional neural network? Okay. So if you look at the traditional machine learning models, they work with the handcrafted features and relatively simple trainable classifiers. So given an object or given an image, whatever is the object, it extracts the handcrafted features, explicitly extract the features from the given image. And then it gives this feature to some trainable classifiers like SVM, random forest, decision trees, whatever it is, and then get the output. So what is the problem with this approach? This process very tedious and costly to develop handcrafted features, and it requires some domain knowledge also. So to extract the right set of features, like for example, in yesterday's class, I have shown you ODI character recognition, and I said that there are 5 important regions of the ODI character. So to understand what are the important regions of the character, you require some domain knowledge. You need the ODI language. You need to know the ODI language, isn't it so? Right. So to explicitly extract the features, you require some domain knowledge, and it is costly operation to develop. Okay, and these handcrafted features are usually highly depend on one particular application. It's not that this is the generalized procedure for each and every domain. So depending on the domain, we have to change this feature extraction. What kind of features that we extract from the given object will be changing from the domain to domain or the application to application. So this is the problem with the traditional machine learning algorithms. So to avoid this problem, in the deep learning, we have the inbuilt automatic multi-stage feature learning process that automatically extract the features from the given image or object. All right. So like for example, here the task is given the image, we have to classify it as the indoor or the outdoor image. So given the image, initially it can extract the low level features. From the low level features, it can extract the mid level features. From the mid level features, it can extract the high level features and use them to train the classifier. So low level features could be pixels or the edges. Mid level features could be the edges of the image or uh, some part of the image, some motif of the image, right? Some high level features could be part or the motif as you see here, right? Something like this. All right. So, so low level features are from the low level features, it extracts the mid level features. From the mid level features, it extracts the high level features and uses the high level features to make a prediction or train a classifier. Fine. So similarly, if you take the face recognition problem, low level features could be the pixels or the edges. Intermediate features could be the part of the face. High level features could be the face. Okay. So like this, level by level, it features are, we are extracting the features that are useful for the training as well as the classification. Okay. So this is the advantage of the convolutional neural network, right, or the deep learning in general. So first we will try to understand what are the drawbacks of fully connected neural network. Then we will start discussing the concept of the convolutional neural network. So I hope you are with me so far. Following, right?
Sir.
Yes. All right. Thank you. So let us try to understand the drawbacks of the fully connected neural network. Let us take a very simple neural network. Okay. Wherein we have 4 layers, one input layer, one output layer, 2 hidden layers. So look at this network carefully. Bias units are ignored. If you want, you can add, that's not matter. So ignoring the bias terms, tell me how many parameters we are supposed to learn in the network. How many weights? Here 4 by 4.
4.
16. Here we have to learn 4. Here one more weight, 1. So total 21, right? 16 plus 4 plus 1, total 21 number of parameters. With a very simple network, very small network, this one. What if the input is an image? What if the input is an image of size 400 by 400 by 3? So this is of size 400 by 400 by 3 and it is a color image. So therefore there are 3 channels in it. So the total number of numerical quantities that this image is representing is 400 times 400 times 3. Suppose if I take the each numerical quantity as an input for the neural network, how many total inputs that we are taking? 400 times 400 times 3, which is 4,80,000 inputs. Okay, so if I take 4,80,000 input units and let the first hidden unit is also taking 4,800, 8,000, 80,000 units. And let the hidden layer 2, at the hidden layer 2 we have this, only one unit. So now tell me, how many parameters this network supposed to learn? How many parameters? How many parameters? 4,80,000 times 4,80,000, which is this. And here how many? 4 lakh
4,80,000.
80,000 plus 1. These many, right? It's a very big number. Am I right? So 4,80,000 times 4,80,000 plus 4,80,000 plus 1, approximately 230 billion number of parameters. This is really huge. Adjusting these many number of parameters to optimize the objective function is very time intensive process, right? So even if I reduce the number of hidden units at layer 1, let us say I made it to 1000. So even then you'll have to learn around 480 million number of parameters. That is also very big. Okay. So one of the problem with this fully connected neural network, especially when the input is like the images or the videos, the number of input data is huge, right? So the input data is huge. So in those cases, the number of parameters that you are supposed to learn is really big. Okay, and it is very time intensive process and it is very difficult to converge to an optimal point with these many number of parameters, right? So that is one of the problem with the artificial neural network. Okay, is that clear? Is this point clear? Shall
Yes,
we move
sir.
on? Yes, fine. So now another one is that it has got little or no invariance to the shifting, scaling or other forms of the distortion. So you see that in the figure, this is the digit class, character recognition problem or character classification problem. See that if I take each pixel as the input, let's say this is a black and white image. If I take each pixel as the input, you see that this pixel is mapped to the first input, this pixel is mapped to the second input and so on, right? So it's not necessary that the A in the image should be at this location only, right? There may be some slight shifts and distortions, right? Like you see that suppose if I move this image 2 positions to the right or left, 2 positions left, then with that small change, 77 of the black pixels are now turned to the white pixels and 77 of the white pixels are now turned to the black pixels. Input, it means the input sequence is changing a lot, right? So it will not be able to recognize this image correctly. Similarly, you see that the other forms of distortion like scaling or other forms of distortion, as you see this, it has got little or no invariance to the shifting, scaling and other forms of the distortion. So this is another problem with a fully connected neural network. Now the question is how the convolutional neural network helps to solve these problems is the question. Okay, so before we're gonna see that what is convolutional neural network, what is convolution, and other basic concept of the convolutional neural network, then we will see that how this convolutional neural network addresses the problems of the artificial neural network. Okay, so what is convolutional neural network? So this is a subcategory of the neural network, and it outperforms all the other models on the image data, especially on the image data. So it is proven to be working well on the image related applications or video related applications, etc. Right? So the architecture of the convolutional neural network is composed of two main blocks. One is the feature extraction phase, the other one is the classification phase. Feature extraction phase and the classification phase. So you see that this architecture has the inbuilt feature extraction mechanism. So feature extraction is not explicit here. It has the inbuilt feature extraction mechanism, and after extracting the features, it is passing to this fully connected neural network and finally giving the classification. All right. So please also observe in the feature extraction phase, we have convolutional ReLU pooling, etc. Here, convolution is a one layer. ReLU, we call it as the activation layer or activation function. So after performing the convolutional operation, we are giving it to the activation function and then giving it to the pooling layer, right? So that means there are three layers, right? So three layers are repeatedly called. One layer is a convolutional layer, second layer is the activation layer, third layer is a pooling layer. So it is going through a sequence of convolutional ReLU pooling operations or the convolutional activation and the pooling layers. And finally, you are getting the extracted features, and this you are giving it to the fully connected neural network. All right. So you see that this is the architecture. The input is passed through a series of convolutional activation and pooling layers, and after that you are getting the features. So these features are passed to the fully connected neural network. So in the fully connected neural network, you have a fully connected layer and the activation function. Series of fully connected and the activation functions it is going through and finally getting the output. Okay. So clear? Are you with me so far? Everybody?
Yes, sir.
Yes, sir.
Okay, fine. So let us try to explore each one of this layer one by one. So let us start with the convolutional layer. So this is another example. You see that this is the input image which is passing through convolutional ReLU pooling layers. So I want you to make note of one point here. Whenever you are applying, the pooling operation is indicated with a red color in the figure, and convolutional plus ReLU operations are indicated with a white color. Fully connected layers are indicated with the blue color, and final softmax function is indicated with the brown color. So please notice that whenever we apply the pooling operation, the size of the image is shrinking. You see that? Have you noticed it that? Right. So it means the intuition behind applying the pooling operation is that to reduce the image without losing, I mean, reduce the size of the input without losing much information, right? So that is the idea behind applying the pooling operation that we're going to see later also. So let us start with the convolutional layer first. So convolutional layer applies one filter or the kernel. So these two terms are used interchangeably in the literature. So we apply a filter or a kernel on the input image. So let's say this is the kernel or the filter that we are applying on the input image. So when you apply a filter, it performs a convolutional operation on the image, right? So this is the input image. We want to classify it as a whether indoor image or outdoor image, or whether it is a kitchen room or bedroom or whatever, living room. Fine. So when you apply a filter on this image, so this is the image, and you see it numerically, it is like some information it is giving about the pixel values, right? So you apply convolutional operation on this kernel or the filter is going throughout the image like this, and then finally you're getting the convoluted image. So please observe it carefully. What it is bringing out, it is bringing out the edges of the image, isn't it, sir? After convolution, the convoluted image is having the edges of the image, isn't it? And the edges of the image is one of the important feature to determine whether it is an indoor image or the outdoor image. So like this, different filters bring out the different aspects or the different features of the image, right? And we can make use of these aspects to train a classifier and uh, train a classifier and then use that classifier to make a prediction. All right. So what is a convolutional operation? So let the input image is this. So each and every pixel is denoted with some variable here, A, B, C, D, to so on F, so on P. Fine. So here, this is the input image, and let the filter is this. So filter is 2 by 2 here, or the kernel size is 2 by 2 here, with the 4 weights W1, W2, W3, W4. So suppose if I apply this filter on this image, how to perform convolutional operation? So the first thing that we have to do is that place the filter on the top left corner. Place the filter on the top left corner. So which means this place, this place. So map the weights with the corresponding variables, right? So when you place the filter, A is corresponding to W1. So multiply A with W1, multiply B with W2, multiply E with W3 and F with W4. Take the sum over that. Take the sum over these multiplications. So multiply A with W1, B with W2, E with W3, F with W4, and then give it to the activation function. And after applying the activation function, you will get the resultant as the H1, and that you place in the convolutional image here. Now shift this filter one position right. Shift this filter one position right, like this, right? So after shifting the filter one position right, again follow the same procedure. Multiply the weights with the corresponding values, and then take sum over that, give it to some function f, activation function f, then you will get H2, place H2 here. So repeat the process. Once you reach to the end of the row, again come below another column. So after completing this row, you come here. It means move one position down vertically, right? Again repeat the process till you reach to the end of the image, right? It means either horizontally or vertically you are moving this filter one position at a time, one row or one column at a time, and then you are applying the convolutional operation. The resultant you are storing in the convoluted image, right? So this is the convolutional operation. You see that here in the top right side figure also you can see. So you're performing the convolution, you're moving it one position right and applying this convolutional operation and then getting the convoluted image. So how many parameters one for one kernel? If it is a one filter of size 2 by 2, how many parameters here? Total 4 parameters, isn't it? So number of parameters for one feature map is 4. Suppose if I apply 100 such kernels or 100 such filters, how many parameters?
400.
400. For each one filter, we have got four parameters. So if you apply 100 such filters, you'll have to learn 400 parameters, right? Fine. So in the convoluted neural network, hidden units are only connected to the local receptive fields. Okay. So local receptive fields, it means unlike in case of fully connected neural network, unlike in case of fully connected neural network, not every neuron in the previous layer connected to every neuron in the next layer, right? So only it connected to the local receptive fields. So let us say each and every entry in this image is one neuron. in the convolutional neural network. So suppose if I take this neuron is only connected to these 4 fields, because after performing convolutional operation with the filter size of 2 by 2, you are getting this output. So it means the output is determined by only these 4 fields, not everyone in the every field in the image, or every entry in the image. So it means this is connected to only local receptive fields. It's not that it is connected to every neuron in the previous layer. Similarly, if I take another layer, this is connected to only the 4 local receptive fields from the previous layer, right? So it means it is only, there is a sparsity of the connections. Not every neuron is connected to every neuron in the next layer. So therefore, it reduces the number of parameters. Okay. So let us try to understand the intuition behind this convolutional filters. So the concept of convolutional has been there since long back in the image processing as well as in the signal processing. But convolutional in the machine learning is a bit different than those in the image processing, right? So what is the difference? Here, suppose these are all the filters from the image processing background. Suppose if I apply a filter on this image, you will get this as the output image, which is a sharp blur image. Suppose if I apply this filter on this image, I'll get this output image, which is the sharpened image. Suppose if I apply these filters on this image, I will get the edges of the image. It means each and every filter is bringing out certain aspect of the image. Okay, but these are the fixed filters, right? But unlike in case of image processing, in the machine learning, we don't fix the filters. We treat them as the parameters, and we model them or learn them using the backpropagation algorithm. It means whichever filter is minimizing the error, it means whichever filter is helping to extract the features that minimizes the error, we learn those filters. So that's the beauty of this convolutional neural network, right? So these kernels or the weights in the kernels or the filters will be learning automatically. We are considering them as the parameters of the network, and we are learning them through the backpropagation algorithm. All right. So understood the difference between the convolutional filters in the image processing and in machine learning?
Yes, sir.
Yeah. So question to you. Suppose you are convolving an input of 6 by 6 image with a 3 by 3 filter. What is the size of the output image?
4 by 4.
4 by 4, great. 4 by 4. So now generalized question. If the input is n by n and the filter size is f by f, what will be the output size?
N minus f into n minus f.
N minus f plus 1 times
Okay.
n minus f plus 1. You see 6 minus 3 plus 1 is 4. Right. So n minus f plus 1 times n minus f plus 1. Right. Fine. So this whatever that we have seen so far is without padding. Without padding means we are not adding any additional border. We are taking the original image as it is and then applying the convolutional operation. So what is the problem with this? What is the problem if I don't apply padding? So if you are applying a 3 by 3 filter on 6 by 6 image, you are getting 4 by 4 image, isn't it? It means the size of the image is shrinking. Hello, am I right?
Yes, sir.
Right. And the corner pixels are given less importance as compared to the central pixels. Isn't it so? Because the corner pixels are involved in the convolutional operation less times as compared to the central pixels. Correct? Right. So what if there is some important feature present in the corner pixel? So let's say you want to classify the birds versus the animals. So one of the important feature to identify birds is the beak of the bird beak, right? So bird beak can be anywhere in the image, right? It can be at the top left corner, it can be at the bottom right corner, it can be at the center, it can be anywhere, right? So irrespective of wherever it is present in the image, it should be able to extract that feature, And convolutional neural network has that quality, but the problem is that you're focusing less at, you're giving less attention to the corner pixels if you don't apply any padding, right? So to avoid this problem, we are padding the image with the some additional border. So there are primarily two disadvantages of not applying padding. Every time we apply a convolutional operation, the size of the image shrinks. This is one problem. Second problem is pixels present in the corner of the image are used only few number of times during the convolutional as compared to the central pixels. This is another problem. So hence we do not focus too much on the corners, since that can lead to information problem. So that can lead to the information loss problem, right? So this is the disadvantage of applying not disadvantage of not applying padding. To overcome these issues, we can pad the image with an additional border. It means we can add an additional pixel all around the edges, as you see right side here, right? So now you see that this is the original image. Now you are applying an additional border of zeros. If the padding size is 1, we are adding one border. If padding size is 2, we add 2 borders, and so on, right? So now if the 6 by 6 image is given to you, if the 6 by 6 image is given to you, if you apply a padding, what will be the size of the image? After applying padding, one additional border all around the edges. If 6 by 6 image is given to you, after
7 by
applying
7.
7 by 7 or 8 by 8?
Sorry, 8 by 8.
Both left side, right side, top
Yes,
and
sir.
down.
Yes, sir. 8
You're
by 8.
adding, right? Total 8 by 8. So now the size of the image is become 8 by 8. So suppose if you apply 3 by 3 filter now, what will be the output size? 8 minus 3 plus 1.
6 by 6.
6 by 6. Okay. So is the size of the image reducing? No, right?
No, sir.
It is still the same, right?
Yes, sir.
So there are two common choices for padding. One is valid padding. It means no padding. Okay. So if we use the valid padding, the output size will be n minus f plus 1 by n minus f plus 1. The other one is the same. It means you select the size of the padding in such a way that output image size is equivalent to the input image size. It means you want this n plus 2p minus f plus 1 is equivalent to n, right? So when you apply padding, the size of the image is becoming n plus 2p. So n is becoming n plus 2p. It means n minus f plus 1 is becoming n plus 2p minus f plus 1. So you want this n plus 2p minus f plus 1 to be same as n. So it means you want to select p is equivalent to f minus 1 by 2. So what is the filter size here? 3 by 3. So 3 minus 1 by 2. What is this? Padding is 1. Got it right? So
Yes, sir.
two choices. One is you don't choose any padding. The other one is select the padding in such a way that the output image size is same as the input image size. So n is equivalent to n plus 2p minus f plus 1. Okay, that means p is equivalent to f minus 1 by 2. So according to the filter size, you can select the pad. The next concept is strided convolution. So if you observe the examples that we have discussed so far, we are taking a stride of 1. It means every time after applying the convolutional operation, you are moving one position right or one position down, right? It means you are moving one position horizontally or vertically every time, right? So suppose if I select the stride of 2, then we move the filter 2 positions right or 2 positions down, horizontally or vertically. We move it 2 positions, not just one position, two steps. Okay, both in the horizontal and the vertical directions separately. Okay, so if the input size is n by n, padding is p, stride is s, filter is f by f, then the output will be n plus 2p minus f by s plus 1 times n plus 2p minus f by s plus 1. Okay, and stride helps to reduce the size of the image and get a particularly useful feature. So you understood, right? So suppose if I give a stride of 2, so after suppose if there is a, let's say, where is this? Okay, so suppose if this is the filter, so after applying this filter, if I take a stride of 2, after putting this not one position, I'll be moving it 2 positions. From here to here, I'll be moving 2 positions. From here to here, another 2 positions. Sorry, another 2 positions from here, right? So if you select a stride of 2, you'll be moving it 2 positions or 2 steps. Got it, right? What is the stride?
Yes, sir. Yes, sir.
Fine. So the next one is convolutional operation over a volume, right? So you see that this is a image of 3 channels: red channel, green channel, and the blue channel, color image. Basically, each pixel is represented with the 3 dimensions: red color and green color and the blue color, right? So now to convolve over the volume, we take the filter size or the number of channels in the filter same as the number of channels in the input image. So how many channels are there in the input image in this example? In this example, there are 3 channels. Am I right? There are 3 channels.
Yes, sir.
Right. So the number of channels in the filter also same, 3 channels. You see that this is a 4x4 filter and number of channels is 3 only. Okay, 4x4x3. So now you are convolving over a 2-dimensional image. You are placing the filter on the 2D image, right? Similarly, you put this 3D channel on the 3D image and apply convolutional operation by mapping the weights to the individual entries of this 3D image. So it means when you perform a convolutional operation at one volume, you get one output. So when you convolve it throughout the image, you get a one channel in the output image. So it means for one filter, you are getting one channel. If you apply multiple filters, you will get multiple channels in the output image. You apply multiple filters, you will get multiple channels in the output image. It means the number of channels that you are getting in the output image is equivalent to the number of filters that you are applying on the input image. And please remember that number of channels in the input image and the number of channels in the filter must be the same. So we'll see an example, then it will be more clear to you. So here is an example of 3D data, right? This is one dimension, this is another dimension, this is another dimension, 3 dimensions of the input image. This is one filter that you are applying. So when you are applying the filter, you see that this part is mapped to here and this part is mapped to here and this part of the filter is mapped to here. Perform the convolutional operation, take the sum over that and give it to the sum activation function, then you will get a particular entry. Now move this one position right and then perform another convolutional operation and then you will get another entry. So like this repeat process throughout the image, then you will get one channel in the output image. Similarly, when you apply the second filter, you will get the second channel and so forth. So please observe that number of channels in the input image is 3. Number of channels in the output image is, in the filter is also 3. And number of channels in the output image is 2, which is equivalent to the number of filters that we are applying here. 2 filters we have applied, that is why we've got 2 channels. So please observe the figure for a few seconds. Then you will, once you observe, please let me know, we will move on. I want you to notice whenever you're performing some operation here, what corresponding entry filled out in the output image. So when you are applying the second filter, it is making changes in the second channel only. When you are applying the first filter, that is filling out the first channel. Clear, right? Convolutional over volume.
Yes, sir.
So if the input size is n by c, nc is the number of channels in the input image. Filter size is f by nc. So please see that nc here. Both of them should be same, right? And padding p, stride s, then the output image is n plus 2p minus f by s plus 1 times n plus 2p minus f by s plus 1 times nc dash, where nc dash is equal to number of filters that we apply. Number of filters that we apply. Okay. So let us summarize one layer of the convolutional network. So we are convolving over the entire image using the filter. Okay, and then add a bias term. This was missing in the process that we have implemented so far. So we actually add a bias term also after convolution. So convolving over the entire image using a filter, add a bias term to the convolution outputs, and finally apply the activation function to generate the activation. So this is one layer of the convolutional network. Now a question to you. Let the input size is 6 by 6 by 3 and the filter size is 3 by 3 by 3. Suppose we have 10 filters. What will be the number of parameters in that layer? How many parameters for one filter?
So 3 cross 3 cross 3 into 10.
3 times 3 times 3 is 27 plus the bias term is there, right? One bias term, we said we are adding bias term. That is not there in the previous procedure that I have shown, but we add the bias term. So 3 times 3 times 3 is 27 plus the bias term 28. So for filter 28 parameters. How many such filters are there?
10.
Into 10.
Into 10. 280 number of parameters. Okay, let me ask you one more question. Suppose if the input size is 100 by 100 by 3 and the filter size is same 3 by 3 by 3. How many parameters you're supposed to learn?
Parameters.
280 only.
Yes, sir.
Yes.
27 for filter plus 1 bias term 28, 10 filters 280. Suppose if the input size is 1000 by 1000 by 3 and the filter size is 3 by 3 by 3. How many parameters you're supposed to learn? Same 280, right? So it means what? The number of parameters that you are supposed to learn is independent of the input image size,
Yes.
right? So isn't it so exciting? Isn't it awesome? Right? So the number of parameters for each filter is 27 plus bias term 28, 10 filters, 28 times 10, 280. So clearly the number of parameters in case of convolutional neural network is independent of the size of the image. It essentially depends on the filter size. So no matter how big the image is, the parameters only depend on the filter size. It's awesome, isn't it? Right. So that's why it is reducing the number of parameters to a larger extent as compared to this artificial neural networks. Okay. So let us see the simple convolutional neural network example with the concepts that we have discussed so far. So this is the input size 39 by 39 by 3. And after applying the convolutional operation with the 10 filters, we are getting 37 by 37 by 10. Can you tell me why 10 here? Why number of channels is 10 in the output image?
Filters.
We have applied 10 filters, right? So the number of channels equivalent to number of filters that we have applied. And why 37 by 37? Because the padding is 0, n minus f plus 1, which is 39 minus 3 plus 1 is 37 by 37, right? Clear, right?
Yes, sir.
Similarly, when you apply 20 filters here with the stride of 2, here we got a 17 by 17 by 20. And here when you apply it got a 7 by 7 by 40. So total how many elements are there here? 7 times 7, 49. 49 times 40 is 1960. So these many features are there. You are connecting it to fully connected neural network. And finally, you are getting this logs, giving it to log softmax function and classifying and finding out the loss. And learning the parameters of the network using the back propagation algorithm, right? It means this filter entry is also considered as the parameters of the network.
Sir,
Ah,
filters will always be square, like 3 cross 3, 5 cross 5.
usually, yes.
It will not be 3 cross 2 or some kind of 3 cross 4.
Generally not.
Generally, 3 cross 3,
Yes,
2
yes.
cross 2.
I mean, when you are mentioning in the programming also, they just ask for the filter size as a number only. It means 3 or 2 or 4, something like this.
Okay.
So now we have completed this convolutional layer. The next layer is the activation layer, right? The activation layer, we know one activation function, that is a sigmoid function. Right, like that there are various alternatives depending on the application and the kind of output that we are expecting and the scaling that we want to perform on the input. We have the different activation functions. Okay, so these are the various options: tan, h, sigmoid, ReLU, leaky ReLU, sine. The most commonly used are for the hidden, I mean the in between layers. ReLU and the leaky ReLU are most commonly used activation functions. The next one is the pooling layer. So pooling layer are generally used to reduce the size of the inputs, hence to speed up the computation. So therefore, it retains the most important information, right? So there are two common choices, but although there are various other variations, max pooling and average pooling. So let us see the max pooling, then you will gradually understand what is average pooling. So this is the input image. Suppose if we apply a 2x2 filter and max pooling operation. So 2x2 filter with a stride of 2. Place the filter here, 2x2 filter. Max pooling means pick a maximum element out of this box. What is the maximum element from this box?
4.
4, right? So put 4 here. Move this with a stride of 2. It means move this box 2 steps. It means the box is now here. What is the maximum element?
5.
5.
5. Now this row is completed. Now move it 2 positions vertically down. Place it here. Right.
3.
What is the max? Next
3. 4.
again
4.
4. So this is the output that you get. 4, 5, 3, 4. Suppose if you apply average pooling, then you will take the average of the elements. 1 plus 3 plus 4 plus 2 by 4. Similarly here, 5 plus 3 plus 3 plus 1 by 4. Similarly here, 3 plus 1 plus 1 by 4, and here 1 plus 3 plus 4 by 4. Like this, we apply average pooling or the max pooling. So with this pooling operation, again we revisit the example here. So when you apply a convolutional operation on the 32 by 32 by 3 image with a filter size 5 and s equal to 1, we got a 28 by 28 by 6 image. So if this is the question to you now, if this is the output image size, can you tell me how many filters have we applied here? What is the number of filters? Sorry, number
6.
6 filters. Yeah, 6 filters. See, when you apply a pooling operation, the size of the image is reduced to 14 by 14 and number of channels remain the same. It means when you apply a pooling operation, number of channels will not change, but the size of the image is shrinking, the other size of the image, right? And when you apply a convolutional operation, depending on the number of filters that you apply, number of channels will vary. The size of the image doesn't shrink that much. All right. So after applying a series of convolutional ReLU pooling operations, we've got 5 by 5 by 10, which is 250 number. This is wrong here, 250 here. These 250 features are passed to a fully connected neural network, a series of fully connected layers, and giving to softmax function finally. Okay, so this is an example. So the input image is given to the series of filters, convolutional ReLU pooling operations, convolutional operation, pooling operation, convolutional plus ReLU, and then pooling operation, convolutional ReLU plus pooling operation, and so on. And then finally you're getting some features. These are given to fully connected neural network, and finally you're getting a classification of whether it is a kitchen or what do you call that, a living room or a bedroom, bathroom, or outdoor image. So this is the classification that this convolutional neural network is doing. Now the question is why we need this convolutional operations. Why we need this convolutional operations. Okay, so there are basically two advantages of using convolutional layer. One is parameter sharing. The other one is the sparsity of the connections. Parameter sharing. Why we say parameter sharing? The same filter is applied throughout the image, isn't it? Right. It means the whole image is sharing the parameters, right? So it is sharing the parameters, and because of that, it has got the spatial invariance property. What is the spatial invariance property? Spatial invariance property means irrespective of wherever the feature is present in the image, this convolutional neural network will be able to identify that feature. So let's say I said one example of classification of the birds versus the animals. So one of the important feature to classify it as a bird is the bird beak. But this bird beak can be anywhere in the image, right? So it can be at the top left corner, it can be at the bottom right corner, it can be anywhere in the image. So irrespective of wherever this feature present in the image, you should be able to identify that feature, right? And the convolutional neural network has that got that capability because the same filter is passed throughout the image. So it can bring out that aspect from the image wherever that feature present in the image, because you are convolving the image with the same filter. The same filter is convolved throughout the image. So it means it will be able to extract the feature wherever it is present in the image. This is one property. The second one is the sparsity of the connections. It means every neuron in the artificial neural network is connected to only local receptive bits, unlike in case of fully connected neural network. So in case of fully connected neural network, every neuron is connected to every neuron in the next layer. But here it is not. It is only connected to very few neurons from the previous layer. Right? Understood, right? The advantages of convolutional neural network.
Yes, sir.
Sure.
Everybody understood? Okay. So madams are silent today. I don't know why. Madams. Okay, fine.
A little bit, sir, because this is fully new to me.
Okay, okay. All right. So please go through the video one more time, madam. You will understand.
Yes, sir. Yes, sir.
Yes. Question to you now. Okay. So here is the question. How many parameters do we require if we use fully connected network for the above example? How many neurons is there at this layer? If I take each element as one neuron, 32 times 3. How many neurons at this layer?
28 by 28 by 6.
28 times 28 by 6. If I apply fully connected neural network, it means all these neurons are connected to all these neurons. How many edges or how many weights? Multiplication of these two, isn't it? Hello, am I right?
Yes, sir.
Yes, sir.
Right. So the number of parameters that you require is 32 times 32 times 3 times 28 times 28 times 6, which is nearly equivalent to 14 million. Makes no sense, right? 14 million parameters between the two layers, right? What if I apply convolutional neural network with a filter size of f5? How many? How many parameters for filter? If the filter size is 5,
5 into 5 into 3.
5 into 5 into 3, which is 75. Okay. So even if I apply 10 filters, it will be only 750, right? Hello? Am I
Yes,
right?
sir.
Yes.
So here, how many filters are applied here? Can you tell me?
6.
6.
6.
6 times 75, which is 450.
450.
Nine. Is it? Yeah, 450
Yeah,
only, right?
450. 450.
450. So even if I add a bias terms, it would be 456, right? So yeah, there may be mistake in the slide. It might have been taken as a 25, right? Yeah, it is 5 times 5 times 3. The channel information is missing here. So total 456. Plus 1 is the bias term. Okay, so total 456. Here are some of the examples of the classic network. It means what I am trying to mention here is that number of parameters are very less in case of convolutional neural network. I hope that point is clear. Clear, right?
Yes, sir.
Yeah.
Right, sir.
So some of the classic networks, okay. So LeNet, which is basically mostly used for the digit classification with using the black and white images. So this is the layer flow, and total number of parameters that the network learns is 60K. Convolutional ReLU pooling, fully connected, and the output layer. Right. This is the layer sequence, and this is the LXNet. Use it for the color images like the object recognition and something like that. This is the layer sequence. The total number of parameters that the network learns is 60 million. And this is the VCG16. This is also famous for the object detection kind of problems. This is the layer sequence. The total number of parameters that it learns is 138. There are many more, ResNet, DenseNet, and all these are there. You can directly use them in the PyTorch library. PyTorch. You can explore this. I'm going to demonstrate some simple program, but you can explore it to the complete text. So these are the various applications. It has got various applications in image classification, like in the search engines, recommender systems, social media, etc. Face recognition is used in social media, entertainment, security, etc. Can be used in optical character recognition, that is used in legal, banking, insurance, document digitization, etc. Medical image computing is used for the risk analysis, anomaly detection, or drug discovery, etc. And there are many more. It is difficult to show a domain that doesn't have the applications of this. Okay, that's all. Thank you very much and happy learning. I hope you understood the session.
Sir, I have a question.
Yeah.
Sir, in one of the previous slide, you mentioned that in this CNN, basically the low-level features, mid-level features, and high-level features are extracted.
Yeah.
Sir, actually, I could not understand actually in which stage these features are weird.
At the low level, what are you taking? You're just taking the pixel information of the image, isn't it? So after
Yeah.
applying convolutional operation, it means you are extracting more solid features by aggregating them in terms of some convolutional operation that you are applying. So if you could visually see that, there's like the edges or there's something like that. Okay, so visually we are not showing them. That is why it is a confusion to you. So let's say after passing it through some convolutional ReLU operations, suppose if you reshape them and convert that into an image again, so it will look like some kind of edges or some part of the image, something like that. Okay. So
Right,
it
sir.
means, yeah.
No, sir. So, sir, after doing convolution, I think we will get the edge information, right, sir?
I mean, it not necessarily that for one application I said edges, right? So if you take the text application, some text application, right? Like summarization of the text. So the low level could be the letters or the words, mid level could be the phrases, right? And high level could be the sentences. to provide the summary of the text. Okay,
Right,
so it
right,
depends
right.
on the application.
Right. So my question is that only, in which stages we will get those high level features basically?
See, which stage means that after passing through some layers, you will get that. Exactly, we cannot tell that. That is to show you that what is the importance of this passing it through series of convolutional layers we have done. But exactly, you cannot tell that after applying a single convolutional operation, you get the edges. After applying another convolutional operation, you get the part of the image like that, right? So it means if you visualize the features after passing through a few convolutional layers, you may observe the edges. After passing it through few convolutional layers again, then you may observe the parts, something like that.
Okay,
So
sir.
if you want to visualize that, you have to reshape that whatever that you are getting the convolutional output, and then just plot the image, show the image like the way that we have shown in. Do you remember in data visualization part, I have shown you how to visualize how to show
Yes.
the images in Python. So
Yes.
using that plt.show, you show that, then you will be able to see that.
Okay. Okay, sir. Thank you.
Yeah. So this is the digit classification using artificial neural networks. Okay. So I'm importing the required libraries. So this is the torch library that I was telling you, PyTorch. Okay, very easy using the torch. There people does it using the TensorFlows and Keras all, but this is the latest. Very easy. So from torch you import the neural network, and from torch vision import the transforms. Transforms is to transform the data into the required format. And this is a data loader to create a iteratable data set. And this is a NumPy library, we know that. And this is the data set that we are importing, MNIST data, standard benchmark data set for the digit classification problem. And from Torch, I'm importing the optimizer to optimize the parameters of the network. And from sklearn.metrics, I'm importing the accuracy score also. All right. So if you want to install the Torch vision, go to the Anaconda prompt and install pip space install space Torch vision and the Torch both. If you are doing it in Google Colab, you need not install anything. You can directly use it. All right. So after this, defining the network. So this is the network that we are seeking. Input size is 784 because the input image size is 28 by 28. So 28 by 28 means total 784 number of pixels. So this 784 number of pixels are the input image, right? So this is the number of units in the input layer. So after that, you are giving it to hidden layer, which is of 124 units. And then you are giving to another hidden layer, which is of 64 units. And finally output layer, and that is of 10 units. Can anyone tell me why 10 units at the output layer?
Sir, because there are 10 digits.
10 digits, yes. So the network is like this. Network is like this. Input image is 784. After that, you're giving it to 128. And after that, you're giving it to 64. And then this is 10. Okay, so this is the network architecture that we are defining here. We're just passing the sizes here, then we will define it here.
Sir,
So the input
here
sizes,
hidden size. Sir, here hidden size are hyperparameter.
hyperparameter, yes. Yeah, not only hidden size, except for the input size and the hidden sizes, number of layers, number of units in every layer, all these are the hyperparameters.
So, sir, we can perform hyperparameter tuning
Parameter
also.
tuning, yes. Yes, you're right. So these are the sizes, 784 by 20, 124, 124 to 64, 64 to 10. Two hidden layers are there. So this is the very simple way of defining the architecture, artificial neural network architecture. nn.sequential I'm calling. Okay. It means we want to execute these layers in this sequence. The first one is the linear layer, which basically multiply the weights with the corresponding inputs. And then you're giving it to the ReLU activation function. The net sum is given to the ReLU activation function. Then the output is again given to the linear layer. It means whatever the output you are getting here multiplied with the corresponding inputs and taken the net sum. And the net sum is again given to the ReLU activation function. Then the resultant again given to the linear function. And finally, you are giving it to the log softmax function. So this is the layer sequence. And this is the input size and this is the output size of that layer, right? So how many inputs it is receiving, how many outputs that it is giving, right? So the first layer is 784, it is receiving the inputs, 124 outputs it is giving. Second layer, it is receiving 124 inputs and it is giving 64 outputs. Third layer, it is receiving 64 inputs and it is giving 10 outputs. It's very simple. Our model is ready, right? So if you have to implement it manually, it takes around, I think around some 150 to 200 lines of code. But you see that within one line you have defined everything. This is one line only, one function. Although I spread it across multiple lines. Okay, just to show it to you. Okay. So now the model is ready. If you want to make the changes or if you want to access the layers of the model, you can access. It's like a list you can access. So this is the accessing the first 3 layers of the model, as you see there, right? So if you want to add any additional models also, you can add it here to this model. Okay, so now after this, you are doing some kind of pre-processing. Here is the transformation that you want is defining here, transforms.compose. You are transforming it into tensor format to tensor and then normalizing the input. This is the mean value for the normalization and this is the standard deviation value. As there is only one channel, we are passing one mean, one standard deviation. If it is a color image, you will have to pass 3 means and 3 standard deviations here, right, for 3 channels. Okay, so here we are loading this MNIST dataset by calling this MNIST that we have already imported from torchvision.datasets. And I set the download equal to true, train equal to true because I am downloading the training data. And then transformation that I am applying is this, whatever that we have defined in the previous line, right? Similarly, test data I'm downloading, train equal to false, transformation, the same transformation we are applying. So the training set is there now, test set is there now. Now I'm calling the data loader to create an iteratable data set. It means multiple batches I'm creating to train the model. Okay, so data loader on the train set, creating batches with a batch size of 64, shuffle equal to true. Shuffle equal to true is necessary for the training data because if you don't shuffle, sometimes you may not get the mix of instances from the different classes. That's why randomly we are shuffling that. For test, it doesn't matter whether you shuffle or not, it doesn't matter. So similarly here also test set, this batch size also doesn't matter. I've taken a batch size of 1000, but it doesn't matter. You can take any batch size. Shuffle equal to false. Okay, fine. So the train loader is there, test loader is there. Now create the loss function. I mean, define the loss function that you want to optimize. Here we are taking negative log likelihood loss function. There are various other options that one can try. And the optimizer is the stochastic gradient descent, SGD. And what we want to optimize, model.parameters, and model is already defined here. Model is this one. So we want to optimize model.parameters and learning rate is this 0.003. Okay, so now we are training the model, right? We are repeating it for number of epochs. You can treat them like the iterations. Number of epochs we defined it to be 5 here. Okay, but I mean, I'm just for the sake of demonstration, I'm creating all this. That's why I've taken very small numbers, but usually we train it for the more number of epochs, right? So in each epoch, we are loading the training data. It means one batch of images and the corresponding targets. One batch of images and the corresponding targets. So this is like a flattening of the image, right? And then initializing the gradients by calling optimizer.zeroGrad, then forward propagation. So model of images means these images are going through a sequence of layers that we have defined in the model. then you get the prediction. So after completing the forward propagation, compute the loss by giving it to the cost function. Cost of predicted comma targets. So cost function is defined here, negative log likelihood loss. So give the predicted and the actual targets that we have got it from the data set here to the cost function. You will get the loss and then perform the backward propagation by calling loss.backward. So very simple, right? This is forward propagation, calling model of the inputs and then performing the loss function, loss at the output layer, and then performing backward propagation. Once the backward propagation is done, your gradients are ready. So update this parameters of the model by calling optimizer.step. So optimizer that we are using here is the stochastic gradient descent that we have defined already. So to add the total loss and print the total loss for once in a while, I mean after completing the each and every epoch. Okay, so you see that these are the losses that we got. Training loss at the first epoch is 1.84. Training loss at the second epoch is 0.74 and the last epoch 0.37. Means each and every epoch the training loss is gradually reducing as we observe there. So now to test it, so that we have defined the model, we have defined the cost function, we have defined the optimizer, then we have completed training also. Now the testing part is pending. So for this we are taking the test loader. So then it means every time we get one batch of images and the corresponding outputs. So batch size we have given away to be 1000 in the test data. So 1000 images and the 1000 outputs you will get. Give it to this model, you will get the output. So select the output that maximizes the probability, right? It means when you get 10 outputs, you will get the probability distributions. Pick up a digit that maximizes the probability. So you will get the prediction in terms of a tensor format, convert that into a NumPy array, and then squeeze it if you have any extra brackets. So this will get it the predicted NumPy array. Similarly, you can also get the actual NumPy array after squeezing. Compute the accuracy score by passing both the predicted and the true values. Take the average by taking the number of batches in the denominator. So this is the accuracy score that we have got. Okay. Similarly, you can implement the convolutional neural network also. I will share the code. Please go through that. I mean, code is already shared anyhow in the drive. Please go. So that's all for today. If you have any queries, I can take. Otherwise, we can wind up the session. Any queries? If something is not clear, please let me know. I can explain it one more.
Sir, one question I have. Recently, I came across this article saying neural convolution is outdated and pooling also, it's not efficient. So, what is your opinion? What is your take on that, sir? Is it outdated, really outdated, or still is being used? Any
Outdated. See, obviously, the technology changes from day to day, sir. Okay. Instead of saying it is outdated, okay, so the concept of this have been evolved. It means it forming the basis for the next level concepts. Okay. It's not that how the concept will be outdated. Maybe the models are outdated, but the concept can never be outdated. So you see that, how do you say, suppose if I say that regression is the concept of the gradient descent is outdated. Do you agree? No, right?
No.
Because we are using that concept only. Either you go for the artificial neural network or some other deep learning, where either that concept only use it, right? Right. Maybe you're making some modifications to it, right? So the concept is remain used, but people may be making some modifications. Like people are now coming up with, instead of taking the convolutional neural network, I forgot that exact word, but they are taking some spatio-temporal location information also, then applying some kind of operation similar to convolution, right? So not exactly convolution, but the idea is slightly changed and applying a different operation on it. But to get that image, what is the basis for it? Convolutional operation only, right? If somebody got that idea, means they found some lacunas with the convolution operation and they've got it. So rather than saying concept is outdated, I would say that concept is evolving and it is continuous process. Sir, Parmesha sir.
Yes, sir.
Sir. Yeah, the
Understood.
evolution is continuous, sir. Anyhow.
Yes, sir. Yeah, particularly they mentioned max pooling is not efficient. I mean, pooling itself, it's giving some side effects, not so efficient. That's why
It
they
depends
have
on the
come up.
application, sir. We can't say that. You see that there are many successful applications in the image processing area that applies max pooling operation only. How can we say that that is not efficient? We can't say that, right? Maybe for a particular application that may not be efficient, particular situation that may not be efficient. But there are situations in which that is efficient also. Okay. That's why it was successful, right? That's why we've been talking about that now. Yeah. All right then. Any other query? Okay then. Thank you very much. Happy learning. Good night.
Thank you, sir.
Thank you, sir.